in there as well. And the guaranteed TCP delivery, like certain UDP protocols like SIP itself can drop certain packets and you can still continue the call. But if you're using TCP, then every packet has to be delivered. With GPRS, the round trip time of like 1 second is nothing abnormal. So again, this is a problem if you're talking, if two people are talking and they're having a very short sentence conversation. Hi, how are you doing? I'm fine. Okay, so how are you? Yeah, that's great. Oh, excellent. Every time you switch per person, you'll get these delays, and they will be really buggy. If you're like me now, presenting with a long monologue, then it won't matter, because if the packets drop, you'll just don't hear me for a while, and then I'll continue talking again. So this is what in the old way was called push to talk, where you actually had to push this button and then you could talk, and then you would say over and you would release the button. So if you're if you're using GPRS, you're very likely have to sort of change the way that you're talking to the other person on the line. Another thing, GPRS uses spare time slots in your service. So if it's New Year and you want to call your mom over your super secure phone, then,
or you're in New York,
or if you're in New York, then forget about calling, because everything will be overloaded, and the first thing that goes is the free GPRS cycles on the cell. Another thing, cell hopping really doesn't work very well. In my personal experience, if you're in the middle of a downtown big city and you take the train and you start your GPRS connection, because in the downtown city area the cells are really small, if you're sitting in a train, the only thing you're doing is reconnecting to a different cell. You're not getting any data through. You're just reconnecting, waiting for the next hop. By the time you're ready to send data, oh, oops, end of cell, next cell starting, so we have to hop again. As soon as you leave the city and the cells become bigger, you actually get some data through. So, but in practice, it really means if you're hopping in a network, it's not going to work as well as a traditional phone call. I'm not sure how the crypto phone, does it have problems with this as well or not? You can sit on a train in Berlin and leave Berlin and keep talking. Okay, so the crypto phone has the same problem, except it reconnects faster than GPRS, so their gaps are less noticeable.
It's important to note that generally speaking, if you've got 150 milliseconds of delay in a conversation, it starts to get noticeable, but it's not too bad. That's what you'd sort of experience on a crummy Skype connection. You hit 300 milliseconds and it starts to become difficult to communicate, and you have to start moving to that sort of push-to-talk mode of communication where you do your little, you give your spiel, you stop, you say over, the next person goes, you wait till they're done, the next person goes. Like, over 300 milliseconds it starts to become annoying, so.
So some people did some serious research over the GPRS bandwidth delays. So even though the title is practical experience with TCP, they actually also did UDP and raw packet statistics. So these are the statistics of 64-byte UDP packets. I'm not sure how visible it is in the back. Basically, it's the delay versus the amount of packets that went through. So basically what they did was they kept the GPRS location stationary. They made sure they had good radio conditions, and then once every 5 to 10 seconds they would send a packet, and then you would see what the packet delay was. And as you can see, the uplink is pretty good, like between 0 and 1 seconds, basically almost all the packets go out. That it would sort of mean that talking on your phone will work pretty well. If you look at the graph on the right, the downlink, you can see that it becomes more and more normal that packets take longer than 1 second, and it's even not uncommon for them to take 2 to 3 seconds. So again, this is where you basically have to go to push to talk and keep keep your talking simple, use monologues, and don't expect too much interactivity from your phone call. Bandwidth-wise, this shows the throughput you can get on GPRS. On the left, the uplink, you can see that, you know, even with poor link condition, well, with poor link conditions, you're gone at, you know, 0.4 kilobyte per second. It's just not going to be enough to have a phone conversation. The same for, I guess, 1.4 for an uplink, I think should be enough. It should be enough if you use a very low codec with a very poor quality.
If you were to use Speaks or G729, I'm pretty sure you could get through on those even with the even with the VPN wrapper.
And you can see that the downlink is not so much of a problem because you're always up in the 4 to 4.5 kilobit range. So how are we going to secure our calls? Well, we sort of already expressed that we like IETF standards and protocols. So first we must secure the voice calls by making a data connection. We also want to have alternatives for things like SMS or MMS and things like internet and email services that people have on certain phones like BlackBerry. So we'll need to decide on a VPN technology that assigns an IP address to your device, because we don't want to use separate encryption mechanisms to secure all these different things. We just want to have our phone have one new internal IP address, and then it will use that IP address per default and then only use encryption, because then the firewall rules on our mobile phone become really easy. Only allow VPN traffic and nothing else. That means that you cannot leak any information by accident. There's only going to be VPN traffic to your VPN server and nothing else. So we're not going to use any homemade crypto. It's somewhat of a lie because we are using OpenVPN, but I'll get back to that. We need to be able to work in badly designed telco networks, and trust me, most networks are really designed badly in the telco world. They don't really do internet or IP networks very well. You'll see weird packet sizes. You'll see a number of layers of NAT devices. You'll see certain packets with certain ports being lost for no reason. Weird ICMP messages. These networks are really dirty. So you'll have to break through it. Sometimes they also on purpose will firewall certain things. We have to go around these firewalls as well. Most people don't realize it, but the reason that Skype is really the most popular default client people use is because it can break out through almost any network there is. It's really good at that. So we need to get some of those features back without, falling into proprietary protocols. And we want the solution to work basically on all platforms, on mobile phones, laptops, and PDAs, because I might want to use my laptop as my phone connection when I can. And also, today we're developing for this phone, and I don't know, tomorrow this Chinese company goes bankrupt or sold or whatever, and they make another phone. Hardware really cycles really fast, and since most hardware needs some hacking of one certain kind before we can actually use it, we want to make things at least, some independent of the hardware we're using, so that we don't have to reinvent the wheel every time a new phone comes to market. So don't make any VoIP calls, only use internet traffic, only use a VPN, run our own operating system, run our own IAM. This is all we've already said before. So this is what our design basically looks like. You have your encryption call from your GSM, goes through the telco cloud that you don't trust but you don't care about anymore because it's only a VPN, goes to your VPN server, and behind that there's a PBX which supports everything you want. If you want, you can reroute the PBX to landlines or other SIP providers, depending on the model of trust you use. We'll come back to that as well. Of course, the VPN server and the PBX and your IM server and your mail server could all be one and the same server, depending on what you want or how big your network is or how many people you need to support, how many phones. If you look at it from the IP layer, The clouds actually work pretty well. Okay. In this case, we picked 10.01.0/24. That's the network on the right. That basically has our VPN server with behind it the other servers. The phones that you see on the left, they get a public IP address. In this case, I called them A.B.C.D and E.F.G.H. Those IP addresses are only used for VPN communication. So they set up the VPN, and then through the VPN you get a new IP address. And you notice that it's in the same range. It's a 10.01 address for both of them. So logically, these phones now appear in your own local company network or home network. And so they will be able to reach each other. So what VPN technologies do we use? As I said, it's really crypto is really difficult. Making your own crypto is really not advisable. The problem with the IETF protocols is they're really clear protocols and everybody knows how they work and they're pretty safe, but they're easily blocked because everybody knows that, if you block UDP port 500, nobody will get an IPsec connection through anymore. So we need to work around that. So on the left, we can see IPsec with LT2P. LT2P is the Microsoft way of tunneling an IP address within a VPN. We decided to use that because it's a standard that sort of works. Even though we don't use any Microsoft products, we are using LT2P for this. The alternative is XAuth, which is an old standard by IETF, or IGV2, which isn't really done yet. So this is a good middle ground for now. So IPsec, it's got a proven track record. It's military grade security buzzword compliant. Works everywhere. It's a standard. Has seen lots of research. It's got good performance. It's really bad to break through NATs. The Linux world is a bit of a mess with IPsec. There's 2 IPsec stacks that haven't been merged yet. One requires a separate patch for NAT reversal. The other one doesn't really handle various packet sizes very well. So basically, when you need to break through a NAT router, things get a bit ugly, and you have a better chance using OpenVPN. So getting back to OpenVPN, it's fairly easy to set up on the client side. It's a bit messy on the server because they're doing various networking hacks on the server to actually route these packets through. If you start to play with it, definitely use a separate server and make sure that your hands can physically touch the server when you're configuring it, because you will screw up and lose your connection to it. It's somewhat homegrown protocol, even though it's using OpenSSL for all the crypto operations. So the crypto itself is pretty trusted, but it's still sort of wrapped up in its own UDP or TCP protocol, which hasn't seen as much research. There's been a few vulnerabilities in OpenVPN, though they have been fixed, both on the protocol and the implementation level. So it's definitely a bit more vulnerable than IPsec is. We prefer not to use it, but we also realize that it has a much better chance of bypassing a firewall than IPsec has. So we basically want to use both of them. Try IPsec, and if that fails, we'll fall back to OpenVPN. So this is another mode where you can use the VPN. Let's assume that you're somewhere in South America and you have your GSM there. You set up your VPN. You don't trust the local place where you are, either the local government or the local big corporation competitor of yours. You can do a VPN connection to your PBX in your trusted country, where you know that the government doesn't eavesdrop on all your calls. Notice that this PBX is in Canada, not in America. And from there on, you can then gate back into the traditional phone system and make an insecure call. So you're protected from the insecure area where you're at, like in this case, South America. And you're only vulnerable to the North American, eavesdropping police, which hopefully has better privacy laws, which Canada actually does. As the slide loads, in this situation, it's more that you don't really care if we're considering here the possibility that you don't really care, for whatever reason, that your government
has the potential to